This is question 9 from MA3A6. It says, let P be a prime and zeta pth root of unity. First of all, show that the pth cyclotomic polynomial is the minimal polynomial of zeta. So that is this polynomial. You could also, write it kind of factorized way like this. And we want to show that it's the minimal polynomial. So first of all, we want to just check that phi of zeta is 0. Well, it is 0 because zeta to the p is just 1. And zeta minus 1, it's non-zero. And so this is equal to 1 minus 1 over something non-zero. And this is 0. Okay, so zeta is a root of phi. Oh, sorry, not just a piece of a primitive. So it's not 1. So technically 1's also a piece root of unity. So we could just pick it like e to the 2 pi I over p. So to show that it's the minimal polynomial, we have to check that it's monic. Well, it's clearly monic. We can see that. Monic means that the leading coefficient is 1. To check it's irreducible, we're going to use Eisenstein's criterion. So Eisenstein's criterion says that if all the coefficients except the leading one, all of them divide a prime p, and the last one doesn't divide that prime squared, then it's irreducible. Okay, but we can't use Eisenstein's criterion right now because these coefficients aren't divisible by a prime because of 1. So what we could do instead is consider phi of x plus 1. So the idea is if phi of x plus 1 was reducible, because right now we're substituting x goes to x plus 1, we can substitute back and then prove that phi is reducible. But in this case, we're going to show this is irreducible, and so is phi by doing the contrapositive. Okay, so what is this? Well, we're going to use this formula. So we get x plus 1 to the p minus 1. X plus 1 minus 1 would be just x. This we can use binomial formula on sum k equals 0 to p choose k, x to the k minus 1 all over x. Okay, so we're going to bring this minus 1 inside. So that's when k is 0. This becomes p choose 0, which is 1, and x to the power 0, which is 1. And so we can just cancel this 1 by just starting the sum from 1. And also we can just divide by an x on top of 1. And this gives us the sum k equals 1 to p, which is k, x to the k minus 1. Okay, so the next thing we know is that we can bring out the leading term. And the leading term would be p choose p, and then p minus 1. So this is plus sum k equals 1 to p minus 1, p, which is k, x to the k minus 1. And we also want the very last term as well. So the very last term here would be k equals 1. So if k equals 1, then this is equal to, well, this is p to minus 1. Plus, if you plug in 1, we just p choose 1, which is p. And then 1 minus 1 is just 0. X is 0 is 1. So we have plus the sum. K equals 2 to p minus 1, p to the k, x to the k minus 1, and finally plus p. Okay, now we want to think about these terms, right? So we want to look at p, choose k, where k is bigger than or equal to 2 and less than p. So for these numbers, we want to check that this is divisible by p. And what's the easiest way to see this? Well, we can look at this. P choose k is just p factorial over k factorial, p minus k factorial. And this top part is divisible by p. And this bottom part is not divisible by p. So any prime that divides the bottom part, it will not divide p. So we'll have to divide some other part of this top part. Because this is an integer, right? This is an integer. So we can just use just normal number theory on it. And so all the primes at the bottom, they must divide. So we can just write this as p minus 1 factorial times p. It must divide p minus 1 factorial. So we can actually just bring this out. And this thing will be an integer, right? Because every prime and the denominator will divide this. And so, this has to divide completely. And this will just give us another factor. And so, P, the point is P divides P choose K. And so P divides every single coefficient, including the final one. But we can see clearly that P squared doesn't divide the final constant term. And so we can use Eisenstein's criteria. And so by Eisenstein, x plus 1 is irreducible, and thus so is the p cyclotomic polynomial. And so we've shown that the p cyclotomic polynomial is the minimal polynomial of the pth primitive root of unity. Now we want to calculate the index of p adjoin zeta in Q. And we know that this is the degree of the minimal polynomial of zeta, right? Which is 5. Okay, well, given this, then the degree of the p cyclotomic polynomial is just p minus 1. It's p minus 1 just from here. That's the highest degree coefficient. And so this is it. So thanks for watching.